So we got to go to the next level, n equals 2. Now n equals 2, we have two sublevels. We have again L equals 0, which is the lower one, and L equals 1, which is 2 minus 1, which gives us a L equal 1 value, which is the P sublevel. So we have the S and the P. If L equals 0, we can only have one ML value, ML equal to 0. But if L equals 1, we have three ML values, negative 1, 0, positive 1. So the next element on the periodic table is lithium. Lithium has three protons. It's got to have three electrons. Well, the first two electrons go just like hydrogen and helium's electrons. But the third electron goes right here, spin up. And it does that, and we know it does that because if you look at the periodic table, which is driven by the quantum numbers, you notice that lithium is it's in the second period on the periodic table, second horizontal row, which is also represents the second shell of the atom, or the second energy level. So it's the first element in the second energy level. There's its electron. So we have three protons. This is where the three electrons would be for lithium. Now, what's important for me and you is to be able to tell me what are the four quantum numbers. It's kind of like, where's the address of this electron? Well, the first quantum number would be 2. The second quantum number would be 0, L equals 0, ML would equal 0, and the last quantum number would be a positive 1/2. So there are the four quantum numbers for the lithium electron. All right. The next element is beryllium. It's got four protons. The first three electrons go just like lithium's, and then the fourth one goes right here, spin down. Now you may be asking, why didn't you put it in the P? Well, you always fill up a sublevel before you move to another sublevel, and that is called the Aufbau Principle, and that's actually in Chapter 8 of the Tro second edition. So the Aufbau Principle says you must fill up a sublevel before moving to another sublevel. The periodic table helps us out again here because if you look at beryllium, the next element is boron. It's in group 13. It's all the way across the periodic table. Well, something's going on here for us to transition all the way across the periodic table. Well, that tells us we're starting a new sublevel, the P sublevel. So boron's electron goes in its own orbital spin up. Carbon's electron goes in the next orbital spin up. And then nitrogen goes in its own orbital spin up. Now you're saying, why did you put them all in their own orbitals? Why didn't you pair them at this point? Well, there's a rule called Hund's rule. Hund's rule says you place the electrons to maximize the number of parallel spins, which means you want them all spinning in the same direction. Another way to think of this is that each electron, like charges, repel each other. They want to be in their own space, in three-dimensional space. So let me draw this. Here's the 2s electrons, again spherical shape for L equals 0. And then we have the 2p electrons. Now p is dumbbell shaped. When we place this in a magnetic field, it splits into three dumbbell shapes. One along the z-axis, one along the x-axis, and one along the y-axis. And so that is the p, x, y, and z that we see here. So by placing one electron in each orbital, the electrons have more space and less repulsion between each electron. If we put two in the same dumbbell shape, that's going to be a lot more repulsion. So you place the electrons in each orbital, spin up first before you pair them in a particular sublevel, and again that's called Hund's rule. So right now we're at nitrogen. We're going to pair the oxygen, then the fluorine, and then the neon. And that fills up the P sublevel. So notice how that works with the periodic table. Groups 13 through 18 will fill up the P sublevel. So we're at neon, and we notice on the periodic table the next element is sodium, and we notice sodium starts the third period. Well, we're also starting the third principal quantum level. So on the third principal quantum level, we still have L equals 0, L equals 1, and now we have a new L value, L equal to 2, which is the D sublevel. If you look back up here, L equals 2 is D. So S, P, D. L equals 0 has one ML value, ML equal to 0, so one orbital. L equals 1 has three ML values, negative 1, 0, positive 1. And L equals 2 has 5 ML values, negative 2, negative 1, 0, 1, and 2. All right. So we're looking at sodium. It's the first element in the third period. So sodium's electron is going to go right here. You got 11 protons, you got 11 electrons. The first 10 go just like neons, and the 11th electron goes in its own. It's the first electron in the third energy level. The S sublevel, which is lower than the P or the D sublevels, and it goes spin up because the first electron always goes spin up, right? And then the second electron would go right here for like magnesium. Magnesium has 12 protons. Here's my 12 electrons. So here's something to remember. The S sublevel is filled up by the first and second groups, except for helium. From period 2 downward, the S sublevel is filled up by the first two groups. Periodic table helps you here because you see we jump all the way from group 2 to group 13 to aluminum, which says we're starting a new sublevel. So aluminum's electron goes here, spin up, and then silicon, and then phosphorus, and then sulfur, chlorine, argon. And we have come to the end of the third period. And so we're about to finish, we're about to go to the next period, the fourth period, where potassium and calcium is started. So N equals 4. We know that potassium and calcium are in the fourth period. So N equals 4 has 4 sublevels. There's something to remember. Whatever level you're in, that's how many sublevels there are. There's 0, which is the S. There's 1, which is the P. There's 2, which is the D. And there's 3, which is the F. And then the number of orbitals, 1 in the S, 3 in the P, 5 in the D, and then the F, remember, it's L equals 3, so ML equals -3, -2, -1, 0, 1, 2, 3. So there are 7 orbitals in the F sublevel, all right? So the potassium, because it's the first element in the fourth period, and we know that the first two groups fill up the S, potassium's electron goes here in the 4s, spin up, and then calcium's goes here in the 4s, spin down. Again, you should be able to tell me what the 4 quantum numbers for that electron are. They would be 4, 0, 0, -1/2. All right, now, here's where the changes occurred. At calcium, we're in group 2. We're not jumping all the way to group 13 anymore. We're going right next to it in group 3, where scandium is located. Scandium is number 21 on the periodic table. So scandium, because there's the bridge here, the transition metals. Remember, a bridge is a transition between two land masses. Scandium's electron goes back into the 3D. So what you got to remember is, when you start the elements in group 3, you are in the D block, the D sublevel, and that D sublevel is always a period behind the level it's located in. So we have scandium, titanium, vanadium, chromium, manganese, all in the 3D, and then we go back and pair them: iron, cobalt, nickel, copper, zinc. Now, once we get to zinc in group 12, the next element is in group 13, and we know that starts the P sublevel, so we go back up here to the 4P, and we go gallium, germanium, arsenic, and selenium, bromine, and argon, or krypton, yeah. And so we can check to make sure everything looks right. There should be a total of 36 electrons, and there are 36. 2 plus 8 plus 18, that's 28, plus 8 is 36. The last electron that we placed in was this one, and that should be in the 4P, and it is. So we have a pretty good feeling that this is the correct orbital diagram for krypton. All right, so one other rule here that we haven't talked about is the Pauli exclusion rule. The Pauli exclusion rule says no 2 electrons in the same atom can have the same 4 quantum numbers. Yeah, they can have the same 3, but they can't have the same 4. Just for example, we've done this one here. It's 4, 0, 0, 1 half, negative 1 half. The other one would be 4, 0, 0, positive 1 half. So there's no 2 electrons in an atom that can have the same 4 quantum numbers, and that's called the Pauli exclusion rule, and you'll need to know that. I hope this helps, and I'll be glad to do more mini lectures if you need help.